So this is the fact file for 2.6 alcohols. We see here there are 6 things that you need to know. The first is to refer to the effect of hydrogen bonding on boiling point and solubility of alcohols with water. Then to classify an alcohol as primary, secondary or tertiary. To recall the preparation of alcohols from halogenoalkanes. To describe the complete and incomplete combustion of alcohols and their use as an alternative fuel. To describe the reaction of alcohols with sodium, with hydrogen bromide and with phosphorus pentachloride. And finally, to describe the oxidation of alcohols using acidified potassium dichromate 7 with reference to formation of aldehydes and carboxylic acids from primary alcohols and ketones from secondary alcohols and the resistance to oxidation of the tertiary alcohols. And yes, there is a typo in there. It should be potassium dichromate 7, not potassium dichromate 6. So alcohols, as you know, all have the functional group OH, which is known as the hydroxyl group, and they're named according to the IUPAC rules. So as usual, you name the longest carbon chain containing the hydroxyl functional group and add the suffix "ol". Then you number the chain so that the attachment is as low a position as possible. And for more than one OH group present, you indicate their numbers with di, tri, etc. and indicate their positions by numbering the chain so that the attachment numbers are as low as possible. And then you indicate the presence of any alkyl groups in the usual manner. So if we look at these two, this is butan 2-ol, and you see here 1, 2, 3, 4, so that's the but. The OH group here for the ol, and it's attached to the second carbon. We could go 1, 2, 3, 4, or 1, 2, 3, 4. So we go in this direction because that gives us the carbon attached to the hydroxyl group with the lowest number, so it's butan 2-ol. In this next example, we have 2,2-dimethyl propan 1-ol. So the longest chain is 3 carbons in whatever direction you go. If you go this way, or even going 1, 2, 3 from top to from the middle to the bottom left. So longest chain is 3, so that's our propan, and then the ol for the hydroxyl group. We want the lowest possible number of the groups, so we're going 1, 2, 3, so that gives us propan 1-ol, and then both these methyl groups are attached to the 2, and it's dimethyl because we have 2 of the CH3 groups. So 2,2-dimethyl propan 1-ol. So we've seen this idea before, that things can be primary, secondary or tertiary, and alcohols are the same. So with primary alcohols, there is one carbon atom bonded directly to the carbon atom that's bonded to the OH group. So you see here, this R group is an alkyl group, and it's on the carbon that has the OH directly attached to it. A secondary alcohol has 2 carbon atoms bonded directly to the carbon atom. Then we see here 2 R groups attached to this carbon with the OH on it. And then this is a typo here as well. It should say tertiary. Some of these fact files have more typos in them than others, but tertiary has 3 carbon atoms bonded directly to the carbon atom. So you see here 1, 2, 3 R groups attached to this carbon with the OH on it. So the effect that has is the boiling point of a particular alcohol is higher than the corresponding alkane with the same number of carbon atoms. And that's due to the ability of an alcohol to exhibit hydrogen bonding between alcohol molecules in addition to van der Waals. Remember, it's not just hydrogen bonding, you have van der Waals as well. So in the laboratory, alcohols are often produced by nucleophilic substitution of halogenoalkanes by aqueous alkali. So alcohols such as ethanol are increasingly used as fuels because they are renewable, they're carbon neutral, and they have high enthalpies of combustion. So the example here is the combustion of ethanol. They completely combust to give carbon dioxide and water, and incompletely combust to give carbon monoxide, water, and sometimes soot, which is just unburnt carbon. So a non-smoky or blue flame is indicative of complete combustion and low carbon content, and a smoky flame is indicative of incomplete combustion and high carbon content. So you need to know some of the reactions of alcohols. The first is with sodium, and you see here that just really substituting the OH for a sodium here. So it's substituting the H and the OH group for the sodium. So what we call that then, we've got ethanol, and that's making sodium ethoxide. And the observations are that the sodium disappears, fizzing occurs, and the mixture warms up. This is exothermic. So then with hydrogen bromide, the whole OH group is replaced and you get the bromoalkane. And then with phosphorus pentachloride, PCl5, you're replacing the OH group with a chlorine, and you're making two other products as well. You have POCl3 and HCl. Now the observations for this reaction are that the solid disappears, the mixture warms up, and you get steamy or misty fumes released. And also there's a hissing noise. So the reaction between phosphorus pentachloride and an alcohol can be used as a diagnostic test for alcohols, as the white steamy fumes observed turn damp litmus paper red, which means that they are HCl. You also need to know about the oxidation of alcohols. So alcohols can undergo oxidation reactions, resulting in a number of different products depending on the alcohol and the conditions used. So primary, secondary and tertiary alcohols behave differently towards typical oxidizing agents, such as acidified potassium dichromate, which is K2Cr2O7, and this can be used to distinguish between the alcohols. We just use this O in square brackets to represent the oxidizing agent in an equation. So primary alcohols, they'll be oxidized to aldehydes, which have this structure. So you have a carbon with a double bond to an oxygen and a hydrogen joined to the same carbon. So for example, ethanol would be oxidized to ethanal. And during this reaction, using the acidified potassium dichromate, the solution changes from orange to green, and there's a change in smell. So it's essential to distill off the aldehyde as it's formed before it's oxidized, because it will be oxidized to the corresponding carboxylic acid. So ethanol would give us ethanoic acid. And the oxidation from the alcohol to the carboxylic acid can be written then as one step. So we see here ethanol being oxidized to ethanoic acid. With secondary alcohols, they're oxidized to ketones, and their structure is shown here. And you notice that the carbonate group, C double bond O, is joined to two, is on a carbon which is joined to two other alkyl groups, so there are no hydrogens there. So during this reaction, using acidified potassium dichromate, the solution changes again from orange to green, and there's a change in smell. And finally, tertiary alcohols are resistant to oxidation.